Okay. So thank you for this opportunity to provide an overview of European policies and research and innovation programs towards the system decarbonization. So this slide shows an overview of the steps towards energy decarbonization in European systems. The whole process started in 2001 with a directive on renewables, and then this was followed in 2009 by the Renewable Energy Directive, setting the RES target for 2020, followed by 2014, another program, 2018, the Renewable Energy Directive, and then it was the Green Deal that set the targets for 2030, 2050. And what you see in the middle is the Horizon programs that support research and innovation for these goals. This slide shows the decarbonization targets that were agreed by the Renewable Energy Directive that show 32% of renewables in gross final energy consumption. The tertiary sector, with increased 25% of total electricity, increased electricity grid use, 40% reduction in greenhouse gas emissions, natural gas below 20%, a robust transition towards CO2 neutral or free gases, EVs, general consumer communities, and residential demand for increased 30% of total electricity, and then hydrogen and biofuels. So that as soon as it was published, very soon after that, there was a new program called the European Green Deal that looked for increased emissions. And then last year, we had published the Fit for 55, which has raised even more the targets to 38 to 40% of renewables in gross final energy consumption, 40% of electricity in heating demand, plus more electric vehicles, 65% of tertiary sector heating covered by electricity, and 55% reduction in greenhouse gas emission compared to 1990, and this is by 2030. And just recently, in fact, in the last few months, there has been another increase of these targets, basically targeting to more independence of fuel, of energy resources, and that was called the Repower EU, where now we speak about 45% of renewables in gross final energy consumption by 2030. And this means doubling the renewables in 2025 and tripling them in 2030. Also providing biomethane and additional hydrogen, renewable hydrogen, doubling the yearly pace of heat pumps to reach 10 million heat pumps in 5 years, rollout of rooftop solar PVs by up to 15 terawatt hours this year. So you see more and more ambitious targets, basically targeting more and more renewables. And just to tell you that in Europe, the renewables are mainly connected at the distribution level, distribution networks. For instance, you look here where the photovoltaic power is installed in several DSOs in Europe. And these are the various voltage levels. In the green lower bar are the low voltage, then the medium voltage, and then the high voltage. And in all European countries, DSOs, 84% of the DGs connected low voltage are PVs. So the very large percentage of this is connected at the distribution network. And if you look at wind power, again, wind power to a large extent is connected to the medium voltage, and some of course, at the high voltage. So wind power is connected by 42% in medium voltage and photovoltaics at 22% also. So the largest percentage of distributed generation of renewables is connected at the distribution networks. At the same time, we have more and more consumers, citizens becoming prosumers, which means operating their own resources, and also smart homes, zero energy buildings. And another concept that is now very much supported in Europe is what we call local energy communities, which are associations, cooperatives, partnerships, non-profit organizations that are controlled by local shareholders. They are generally value rather than profit-driven. They are involved in distributed generation and in performing also distribution system activities. So you see that more and more the system becomes more decentralized and more complicated. And this also is increased now by the impact of electric vehicle charging on the grid. You see that the number of EVs in Europe is increasing in the first chart. And you see that now both the power hybrid, the plug-in hybrid, and the battery have reached about 1,700,000 cars. You see that also the electric light duty vehicle chargers are increasing, both at public and also private level. And you see very ambitious plans. I know, of course, that China is very much advanced in this area. You have a fantastic activity in electromobility. However, also Europe is in the same path, following the same path. So what I want to say is that this makes the system operation much more complicated. And what is mostly complicated is that the distribution system, where now has many more distributed sources, as you saw before. It has more wind, more PVs. It has more EV charging, demand side participation. Also, energy storage is becoming more and more connected. And this requires, of course, sophisticated techniques for active network management. So all this evolution is mainly centered in the electricity networks in transition. And in fact, all this high variable renewable generation distribution network creates a number of challenges. Let's say in the steady state, we have reverse power flows, where local DG exceeds the local demand. We have voltage rises at the remote buses. We have additional power flows in the transmission system. You know, in Greece, in Europe, transmission distribution are unbundled. So transmission systems do not really know what happens at distribution level. So they suddenly see flows coming from the distribution system that they were not expected, reverse power flows from the distribution system. And the transmission capacity use is also problematic because you have lightly and highly loaded periods during certain dispatch periods, and that means you need to enhance networks that are not fully or very well exploited. And then the dynamic state, you know the problem of reduced inertia, increased frequency excursions, since you have reduced rotating masses. There are impacts on grid stability, both angular and voltage stability. And also, since you have different cutoff frequencies for renewable disconnection, you might have disconnections that will affect the instability in the system, the stability of the system. These are some examples of challenges. You know this famous duck curve, where you have high ramp-up requirements as photovoltaics are penetrating the system. And then you can have also high voltages at the high voltage buses, more and more going close to the maximum voltage profile and increasing much more than the expected voltage. And this creates monitoring and control becoming more volatile, more volatile grid parameters like voltage and frequency, how you can manage increasing line and substation aging due to more volatile power flows, how you can redispatch self-consumption and distribution, to manage grid parameters in real time, facilitate the integration of greater variable generation, and enable operation of renewable generation also at distribution level. And the power challenges can be summarized in this triangle, where you have problems in investment planning and execution. So how you can optimize investments, how you can ease investment execution because there are a lot of oppositions, to security of supply and automation, how you modernize the grid, how you enhance grid stability, you increase resilience, a very important issue because also of the more and more frequent weather disasters, how you enhance data and data management and cybersecurity, and the energy transition, how you integrate variable renewable generation to enable demand-side participation, integrate distributed resources, as I showed you before. And as I said, these are, to a large extent, problems of the distribution system today. So what you see here is that the investments that have been estimated by distribution networks until 2030 are increasing. So you can see that the investment needs for distribution will increase in the last 10 years by 50 to 70% at an annual rate of 40 billion euros. And you see here how this money is attributed to the various sectors of distribution. So some part is attributed to the buildings and electrifying buildings, and I mean how you use the flexibility of buildings and industrial processes, how you use electrifying mobility, and then how you support emission-free generation. And a large part is some funds are attributed to resilience, to increase the resilience of the system, including storage and other technologies. And one very large part is attributed to modernization, digitalization, automation, and smart meters. So let me focus a bit on that. So you see that it is important that modernization and smartening of the system is more and more important. Modernization, we mean replacement and modernization of grid assets, like lines, transformation centers, to maintain the high level of robustness, to strengthen the system against natural disasters and make them more controllable. Automation of substation and transformer stations, automation of substation distribution level, including remote control of substations, monitoring, very important because monitoring, as you know, lacks a distribution system, especially at the lower voltage levels, and data management. And smart meters, this is a very important project that not all European countries have advanced very effectively. There's already in some advanced countries, they are already in the past second generation, but it is important, as you know, to enable consumers to monitor their consumption and participate also as active citizens. So this is calculated to be about 170 billion euros. And I remind you that we said we need 440 billion euros per year for the whole investments. So let me focus a bit on the digitalization of the system. Now there is huge amounts of data available at the distribution system that can lead to the digital transformation of the DSOs. So DSOs are becoming more and more data-centric companies. They need to manage millions of daily real-time signals that come through satellite, power line communication system, radio, fiber optic lines, other communication technologies. You have data coming from the smart meters, data coming from the smart transformers, data coming from sensors throughout the system. And this can be used for operational planning of the system to improve a lot its security and also its effectiveness, its efficiency. Here's a number of examples where these technologies can be used for distribution networks, including how you can use big data for local balancing of supply and demand, how you can have data-driven asset strategies to for preventive and condition-based maintenance and predictive outage, how we can use smart meters for distributed sensors that provide the state of the system, customer interactions analysis, personalized communication. How we can provide platforms to support local markets and distributed energy resources and marketplaces, to use it for back office automation, to use it for field workforce who can have access to maps, data, real-time expertise, and also to have a high level of situational awareness to enable energy balancing. Also here you can see the application of digital twins and other technologies. So a lot of applications that can help the distribution system operators optimize their system operation. One of the biggest problems of nowadays systems with a high level of renewables is the challenge of flexibility, because as you have more and more variable renewable energies and distributed energy resources connected to the system, they decommissioned conventional power plants. And this means that there is a need for flexibility that was provided traditionally by the large thermal generators. So now that you need more flexibility, the thermal generators are retired, and you have to exploit the local flexibility provided by distributed resources. And this means really a close collaboration between TSOs and DSOs and market parties. This is very important to avoid system disturbances. You need efficient data exchanges between TSOs and DSOs and market parties, and different markets, flexibility markets, balance, congestion management, etc. So this is a very important development. And especially at the distribution level, where I said that most of the distributed energy resources, flexibility resources are now connected, you need intelligent networks that must be able to procure flexibility delivered locally on the market or through direct contacts with flexibility providers, and help all this make the system operate. And there's a number of efforts now in Europe that really try to experiment on how grid services can be provided. This is an example of the European project called Coordinate. And you see where the TSOs, that is responsible for the balancing, initial response, condition management, voltage control, black start, and the DSO, who also has its own resources to manage congestion management, voltage control at local level, at the distribution level, to help in black start and control by loading. All this should collaborate to provide services through a flexibility service provider. And there's a number of products and a number of markets that have been proposed and experimented on how this coordination can be effective. This is an example of products regarding balancing, congestion management, voltage control, response, black start, etc. And another, so what is an idea that is now discussed in Europe is what is called subsidiarity principle for energy systems. And this means that energy are operated in such a way that actions are optimized locally at the most immediate level, and actions that cannot be handled locally are handled at the next level. So this brings the idea of regions that are dynamically sized and cell-based, and a microgrid is a typical distribution network structure that satisfies this requirement and can be seen as the best way to organize local energy resources. And by interconnecting multiple microgrids, you can also think of another way of developing the system. This idea brings significant benefits, and amongst which local balancing of energy and demand, without causing excessive flows and congestions, and reducing the need for infrastructure investments. And of course, you all know what is a microgrid, and this is just a reminder of the definition, which are electricity distribution systems that contains distributed energy resources. can be operated in a controlled, coordinated way. It can be connected or islanded, and this, of course, provides increased flexibility and increased resilience of the system. And this is, of course, a very basic concept in current and future electricity networks. Microgrids can provide a large number of services for operators. They can provide peak saving, voltage control, islanding operation, black start. These are ancillary services. And they can also offer service for electric vehicles. For example, fast charging at dispersed location. You can have optimal placement of charging stations or generation resources. You can have low-cost generation mix for fast charging of EVs and truck fleets. Optimal charging and discharging of electric storage and EV fleets to minimize costs and mitigate the impact of grid outages so the EV charging schedules are not affected. And another important issue is, of course, the challenge of resilience, where you see here the picture of the European megagrid. European megagrid aims to exploit the very rich potential of wind in the North Sea through offshore wind and the very rich potential of solar potential through large PV stations on the southern Europe. And this, of course, needs an efficient and effective high voltage distribution transmission network to transfer this energy to the main consumption centers. However, so this has obvious advantages. However, such a system also are more vulnerable to catastrophic events due to climate change. And you can see that there are two ways now to protect the system. One way is to provide a redundancy in assets, building more and more stronger and more robust assets, or also use intelligent operation. And microgrids, which really provide smart network technologies, demand response, flexible DG distributed generation and storage, can help the system to strengthen its resilience against these catastrophic events. And of course, this requires intelligent control techniques and in fact, application of intelligence in the system. So if you look at the various measures that can be used for resilience, you have a number of hardening measures, like undergrounding distribution lines, upgrading poles and structures, elevating substations for floods, relocating facilities, and having alternative transmission routes. You can also have smart measures using distributed energy systems, distributed generation, demand-side management, centralized control, preventive control, of course, having a good weather forecast, network configuration, microgrids, and also advanced adaptive restoration. And this figure shows how microgrids can be used to support the resilience of both transmission system by providing local support and also distribution systems, either having supporting the whole distribution line or splitting into self-sufficient microgrids, or even microgrids itself. They can help resilience and especially restoration. So this completes my overall picture of the European landscape of future and current systems and the basic problems that are faced. And now let me devote a few minutes for research and innovation. So Europe is supporting research and innovation through these framework programs. We have started as early as 1984 with Framework Program 1, and now it has moved to today. It has moved into Horizon through Framework Program 2, 3, 4, 5, 6, and 7. The later one was in Horizon 2020, and today there has been in that Horizon Europe, that is something like 100 billion euros, And this is, of course, the very large program with a lot of funds devoted also. This is for the whole area of research, of course, but in the Horizon Europe, 15 plus billion euros are devoted for research and innovation for climate, energy, and mobility. And so now is the moment where the European Commission is planning how this money will be spent on which areas of research. And the European Technology Innovation Platform, Smart Greeks, for Smart Network for Energy Transition, this platform, this organization, has been set up by the European Commission to guide and identify sustainable innovation priorities, support the Europe's energy transition. And this goes not only for electricity, but beyond smart electricity grids, also to encompass all energy carriers. And this platform brings together the main stakeholders of the European energy field. As you see in the left part of the slide, it has organizations, associations of transmission system operators, distribution system operators, national representatives, research and academia, storage, consumers, thermal generation, renewable generation, ICT, equipment manufacturers and suppliers, interface with other energy carriers and regulators. So representatives of all these organizations are working together. There are more than 350 experts that collaborate to prepare visions, roadmaps, and implementation plans for the research and innovation programs. And the important thing is that they provide a consolidated view. So all these people sit together and manage to agree on what should be researched in the next periods, in the next years. And ETIPSNet has published its Vision 2050 in 2018. And this is depicted in this infographic that shows several elements of the future vision. In summary, this means that the main production generation will come from renewables, mainly concentrated in distributed renewables, and also thermal and heating networks, synthetic gases and hydrogen, and all this will be provided by renewables. You see a flexibility portfolio with several resources, storage solutions, integrated energy networks, sector coupling, and digitalization, very important to support this operation. This is also a nice slide that shows how the various components will be organized. Generation, as I told you, it's mainly renewable generation, also renewable electricity and heating and cooling, renewable gas, renewable fuel, some nuclear. And then for energy consumption, you see, of course, the typical households, tertiary sector, and industry and agriculture, also very large electrification of the ground transport, electromobility, maritime and aviation. And in the middle, you see the networks, not only electricity, but also gas networks, thermal networks, and liquid fuel networks. And these are interfaced through conversion technologies and also local storage. And electricity networks is the backbone of this integrated energy system, as the electricity networks are the more versatile and flexible networks. And this vision is supported by that Vision 2050 is supported by 10-year roadmaps, and every roadmap is subdivided in a number of implementation plans that have a 3-year horizon. And these implementation plans are used to help the European Commission to decide to procure the new research and innovation programs. So at the moment, we have completed the next implementation plan of 2020 to 25 in the context of the new roadmap. And what we have used as basic elements is what we call high-level use cases. And high-level use cases means families of projects, of priority project concepts that can be used in order to provide bits of the various organizations on what can be done. And just let me give you an overview of these high-level use cases. So far, we have thought of 9 high-level use cases with indicative budgets and for the next IP. So these are the optimal cross-sector integration and grid-scale storage, the various energy sectors, how they can operate and integrate also with grid-scale storage. The high-level use case 2 is about TSO, DSO, and system user interactions, which means mainly how you can use flexibility, as I explained to you, to operate the system at the distribution level and also by system users. The third high-level use case speaks about markets, all types of markets, pan-European wholesale markets, but also regional and local markets, because the models of the markets need to be reconsidered with increased penetration of renewables. High-level use case 4 is about massive penetration of renewables, also transmission, distribution grid, transmission with a high penetration of offshore wind and other large installation at the transmission level, but also distributed resource at the distribution level. The digital technologies for market participation of consumers, again, very important element. Secure operation of widespread use of power electronics at all system levels. Here you have the use of power electronics also as power electronic interfaces at transmission level. We want to investigate the grid forming inverters, how you have large HVDC networks, also low voltage DC, medium voltage DC, hybrid systems, etc. How you enhance system supervision and control, including cybersecurity, the new control centers, the new EMS systems, also distribution management systems, transportation, integration and storage, electromobility, and also, as I told you, ships and aviation. And then how you can use the flexibility of buildings, district and industrial processes to help operate the system. So this is an overview of what we have thought of research for the coming 10 years. And this is further described and specialized in specific project families of projects. So this concludes my presentation. I want to thank you very much for your attention. And of course, if there is any question, I'm happy to